Hi, Dave.
Hello, Adele. How are you?
I'm good. How are you?
Doing well. Doing well.
Wonderful. All right, Papa.
Have you seen my mug? Yeah,
Yeah, that's what I'm referring from. I should have put my Papa t-shirt.
yeah. It's it's so much. Oh, there you got it too. Good, best papa ever. Yeah.
Oh yeah, best Papa ever. Yeah, of
All
course.
right. Well, I should have. You won today. I didn't have my cup, so you are the best papa. Yeah, it's a pretty good job when you could get it.
Yeah, you know, uh, I don't know how much you know this, but they say in Iranian culture, they say that kids are almonds with the shell, and grandkids are the inside the shell,
Ah,
know.
that's wonderful. I hadn't heard that. That's wonderful. So, do they live close by?
Yes, actually, within really 8 to 10 minutes of us.
Yeah, that's
Yeah.
fantastic.
And yours?
I have seven, so as close as about the same 8 to 10 minutes. But then I have one granddaughter who lives in Germany with her
Oh, okay. That's a little bit far away. Yeah.
a little bit far, and then two in Frederick. Not
Oh,
that.
okay.
Yeah.
Yeah, all right. Well,
Yeah. Hello, Rahat. How are you?
I'm good. How are you?
Good, good, good. Yeah, Fernando.
Yeah, for some reason, something strange happened. The invitation disappeared from my calendar on my computer, even though it's on my phone. So I don't know what's going on,
Huh.
and I can't retrieve it. And and I'm trying to find a good way to get it from my phone to the computer.
You want me
I'll,
just to email you the connection?
yeah, if you can email me the link, then
Yeah. Well, I'll
it
do
should
that.
work out. Because sorry about that.
No worries. That's strange.
I have no idea why.
All right. It'll come to you in about a minute or so.
Yeah. In the meantime, I'm here, so it's all good.
Um,
And also, in the meantime, I hope everybody's doing well. That you had a good week, and that the meeting ahead is a good way to wrap up the week for each one of you.
What planet are you living on?
So right now in Planet Bethesda, so it's not too bad.
right, Fernando, it should be coming your way.
Right, all right. I'll wait for it. We can just keep going, I guess.
Yeah. Um, Rahat, you should probably. Oh, you are recording. Okay, great. Great. Okay. Well, I think we're ready to go, Fernando.
Yep.
It actually started recording when I logged in, so I'm not
No,
sure.
that's great. No,
Okay.
that's perfect.
Yeah. So let's just do a quick rundown of the agenda and roll it out.
So we have Mike Evans, who's joined us today from the Chesapeake Conservancy, who's going to be giving us a presentation on on small scale analysis, and will be this will kind of fit in to the overall concept if we end up, working on sort of the analysis of impacts to Maryland. I think some of this work, overall impacts of climate change on Maryland, if we end up updating that, this work, I think, can help lend to it. After we learn more, we could discuss it. And then following that, we're going to have a conversation that Mark Stewart's going to help us lead related to zero emissions and the upcoming plans that they have with a group from University of Maryland, and then after that we could have some more discussion going from that. So there you go, Fernando. And I don't know if you want to just take here and do recommend introductions or not. Or...
Sure. Yeah, maybe we can do a quick run of introductions. I do notice a few new names or names that I haven't seen before in this group. So we can do that very quickly. Two comments on the agenda. Thanks, Mark, thanks, Mike and Mark, for leading discussions today. With respect to the second discussion on the net zero, in the recent Maryland Climate Change Commission meeting, we had a very good presentation by University of Maryland's Center for Global Sustainability that I think is very relevant to topics that we have been discussing as to planning scenarios for the state of Maryland around climate change and having the analytical tools to get some meaningful answers. So I think we'll focus on that. So yeah, so why don't we just do a quick round of intros? Let's start with Dave and then Adele.
Sure. Yeah, Dave Namazi, University of Maryland Center for Environmental Science, and I help staff the STWG.
Yeah, Adele and then Robin.
Adel Shir Mohammadi, University of Maryland, College Park, Department of Environmental Science and Technology. And I do teaching and research all related to climate, non-point source pollution, wherever I can find money.
All right, Robin and then Jared.
Robin Gilden, University of Maryland School of Nursing. I teach environmental health and public health, and I am a commissioner representing public health.
Thank you. So Jared and then Rahat.
Hi there, I'm Jared Williams with the Maryland Department of the Environment, and I provide support to the Commission on Climate Change.
Okay, great. Thank you, Rahat. And then Mike.
My name is Rahat Sharif. I'm a state science policy fellow here, and I'm also a PhD candidate at the University of Maryland at environmental science and technology.
All right, Mike and then Mark.
Hey, everyone. I'm Mike Evans. I'm the Deputy Director of the Conservation Innovation Center at the Chesapeake Conservancy.
Thank you. Thanks for being with us today. Mark and then Don.
Good afternoon. Mark Stewart, Climate Change Program Manager at MDE.
Thank you, Mark. Don and then Suzanne.
Don Bosch, Emeritus Professor at University of Maryland Center for Environmental Science and an 18-year veteran of this committee, of this working group.
Oh, wow. All right, Suzanne, then Scott.
Suzanne Dorsey, Deputy Secretary, Maryland Department of the Environment.
Thank you, Suzanne. Scott and then Eric.
Hi, everybody. Good afternoon. Scott Kanaki here. I'm the director of the Morgan State University Patuxent Environmental and Aquatic Research Laboratory, and I'm an environmental economist by training.
Great. Eric and then Rachel.
Eric Waxman. I'm director of the Maryland Energy Innovation Institute and a professor at the University of Maryland, College Park.
Thank you, Eric. Rachel and then James.
Sure. Good afternoon, Rachel Lamb. I'm Secretary McElwain, Senior Climate Advisor here at the Department of the Environment.
Thank you, Rachel. James and then Cindy.
Hi, I'm James. I'm a data analyst in the climate change program in MDE, and I'll just be mainly listening today.
Thank you, James. That listening is all good. Cindy and then Scott W, because there's two Scotts.
Good afternoon, Cindy Osordo, policy analyst with the Climate Change Program, and I couldn't help but share a good news piece in the chat. There was the release of the Clean Air Report by our agency this week in celebration of Earth Day. Thank you.
Thank you, Cindy. Scott W.
Yes, good afternoon, Scott Waitlovich, and I too am just listening in. Thank you.
That sounds like a plan. All right. So I guess then we move up to Mike's presentation discussion.
Mike, I made you a co-host, so you should be able to share your screen if you're familiar with Zoom.
I am familiar with Zoom, although that doesn't mean that I can always share my screen on demand. But I think I see the button, so we'll give it a whirl.
Great.
Yeah, hold the presentation. Let's see. Yeah, it's back. Okay, we're gonna get a brief infinity window.
Yeah, it's coming up.
Yep.
There you go. Great.
All right. Everybody can see a beautiful picture of a mountain stream landscape.
Yep.
Great. Awesome. Well, I am really excited to be here. I appreciate the invitation to come and share some of the mostly data tools that the Conservation Innovation Center at the Chesapeake Conservancy has been building, all directed towards this goal of precision conservation. And I'm going to be going through really just some examples of our cornerstone data sets that we've released, and then ending on a little bit of a sneak preview of one of the data sets that we are most excited about that we just completed a pilot project on. So just in case folks are not familiar with the Conservancy, I know we're a relatively small organization. We're focused on the Chesapeake Bay watershed in this region. And our goal, like many others in this work group, is to conserve and restore the natural resources of the Chesapeake Bay. And we work primarily in really close partnership with the Chesapeake Bay program, the collaboration with federal, state, and local agencies that are all working to implement the Chesapeake Watershed Agreement. But we also collaborate with academic institutions, as well as a lot of different, even more locally focused land trusts, watershed groups, those types of organizations. And our main role in a lot of these collaborations is to be data providers, usually to help some group better characterize and understand the landscape that they're interested in. And like I said, everything that I want to share today to give a flavor of what some of those data sets and tools look like are all sort of falling under the umbrella of tools that can improve precision conservation. So what I mean when I say this is can be kind of explained simply by the quote on the screen. We want to be able to get the right actions in the right places at the right time. And so to do that, we need very accurate, but also very precise, spatially refined data so that we can make sure that our efforts and the efforts of our partners are maximally efficient and effective. So the first data set that I'm guessing folks on this call may be familiar with, that I'll talk a little bit about, is our high resolution land use land cover data. We've been producing this for a number of years now, and we have 3 going on 4 vintages of those data. I will share our other, I think, spatially widest ranging products as well. We recently finished a project leveraging AI and a bunch of remote sensing data to create a method for updating wetland maps at high resolution. And in many cases, trying to see if we can use that to replace NWI data or improve NWI data. We've also created a high-resolution hydrography data set. So this is mapping streams and ditches with greater precision often than what is authoritatively available. And then the sneak peek, the glimpse into the future of what's coming next is we just concluded a pilot project trying to improve the Chesapeake Bay land change model. I slow down there. It's a mouthful. I'm trying not to trip over my words. CBLCM for short. And this is a model that produces data anticipating where commercial and residential development happen in the future. So that's the menu of what we're going to go over today. I'm not going to go really deep into the methods, but I'm happy to answer any questions that I can about how these data are produced. My goal today is really to focus on what we've put out there and how it's been used. And my hope is to spark ideas and discussions about how you all see any of these data sets or tools being useful in your own work. So to start, our probably most well-known data set is the 1 meter resolution land use land cover data. So this exists for all 205 counties that cover or that intersect, the Chesapeake Bay watershed. and it maps land cover into 12 classes, again at 1 meter resolution, and converts those land cover classes based on ancillary data sets that we've acquired from partners into 54 land use classes. And so I think, land cover is one of those seemingly ubiquitous, very familiar data sets. And so there's any number of applications I'm sure that you all can imagine these get put towards. The ones that we have seen get the most use among our partners is to quantify changes in tree cover, often in association with carbon sequestration goals. We've also seen the data used for plantable area analysis, trying to identify places where trees can be planted, either to buffer riparian corridors or sometimes also in service of carbon goals. The data get used in a bunch of different parcel prioritization tools by organizations that are trying to identify the ideal parcels to invest in protection. And then the Chesapeake Bay program uses these data primarily to track development and other changes to the landscape. So the reason that these data are so widely used is because before they were available, the best available land cover data at this scale and extent was the 30 meter resolution national land cover data set, which you're seeing flash up on your screen here. And you can see when we're talking about precision conservation, the 1 meter product that then appears just offers much more detail and refinement of classes for conducting the analyses that I just mentioned with much greater precision. And when you're talking about analyses that result in parcel prioritization, we found that level of specificity is really important. So another illustration of what these data look like in terms of tracking change. As I mentioned, we've produced these data sets for 2013, 2017, and now 2021. And we have an agreement with the Bay program to update and produce data for 2024. So this also lets us track change in land use between those time periods. So an example of what those change data look like, again, they're at 1 meter pixel resolution, and we can classify transitions based on the previous land cover class and the next land cover class. So here we're looking at the development of a large residential area between 2013 and 2017 in Frederick, Maryland. So these data, like I said, are publicly available. You can access them either through Sciencebase from USGS, or we've also made them available through WebViewer. And if you want to just sort of check them out, you can use the link below. And we provide a web view that also has county by county data download. So this is the best way to kind of get a quick visualization and an overview of these data. Okay. So building off of our efforts to map land cover generally at 1 meter resolution, we a couple years ago identified and basically had reported to us by a number of different partners the need for more precise, accurate maps of wetlands specifically. The land cover data does not capture non-tidal forested wetlands particularly well. Those get wrapped into a forest class. And as folks on this call know, wetland maps wetlands are a really important land cover class for a lot of regulated activities. They're really in a lot of compliance cases, and also in a place like the Bay watershed, where water quality modeling is such a big part of what many groups do. Wetlands play an outsized role among land cover classes. So we really saw this need. Folks were expressing that depending where you are, NWI data or other local data sets were either insufficiently consistent in their availability or oftentimes out of date. We work with groups in Pennsylvania, and some of the NWI data sets up in that neck of the woods are from as far back as like 2012. And so you can imagine the landscape has just changed a lot since then. So I'm going to go a little bit into a little more detail with our wetland mapping, because it is a great case to illustrate not only a data set, but a workflow that we've developed to map things generally in the watershed using the intersection of remote sensing data, custom-built AI models that we've been developing, and cloud computing resources. So as I show the data products, I'll also pull the curtain back a little bit on how we generated these wetland data. So we are leveraging deep learning, and when I say deep learning, what I'm talking about are models that use neural networks, which I'm showing a diagram of here. And the reason that we use this to map wetlands is because these networks are really good at learning nonlinearities, conditionalities, and complex interactions among predictor variables. And so like any other model, it's taking a set of predictor variables on the left. In this case, I'm showing the different reflectance bands from a remote sensing image, and it's making some sort of prediction. In this case, we want to categorize pixels into different wetland land cover types. And this sophistication of model we thought was necessary to accomplish this task because of the variability of wetlands through space and time, what they look like, what variables correspond to wetlands in one location versus another. And we can also organize deep learning models to learn and understand spatial context. So by arranging the weights of a neural network into convolutional kernels, which I'm showing here, these matrices of weights can learn to interpret shapes, gradients, edges, boundaries, things like that in an image. So we have this powerful network to understand all these potentially complex interactions between input variables, and we can arrange the weights of that model so that it's actually learning spatial context. Again, thinking that that would be important to get this sort of tricky land cover class mapped. So at the end of the day, what we developed was a model that can take remote sensing data, an image like this, and basically delineate non-tidal forested wetland classes. I realize this is a tidal example, but just for illustration purposes, that's the goal. And so we did this by training a model with thousands and thousands of examples of delineated wetlands and a variety of remote sensing data. We used NAPE imagery, the Surgo soil characteristic data set, and digital elevation data. Trained our model to take those and identify where wetlands were. So this is an overview of the training process, which we leveraged Microsoft Planetary Computer for accessing remote sensing and other geospatial data sets, trained our models in the cloud, and then used them to predict and make maps of wetlands. Once we had a model that was performing adequately in terms of mapping wetlands in some test areas, we were able to apply it to a case of 14 counties across the watershed. And so just an example of what those outputs look like compared to NWI data. In one example, I think this might be in the Eastern Shore. And the reason, again, just highlighting sort of the usefulness of not only these data, but the technique is now that we have this trained model, we can use it to reproduce or update maps of wetlands very quickly whenever new data comes in. And so the examples that I'm showing here kind of illustrate the need to update our maps more frequently than maybe they have been in the past. You see along the left column there, some existing NWI data where clearly the landscape has changed since those wetlands were mapped. And our model now running over those same areas identifies much more reasonable boundaries of wetland areas. And similarly, it seems to be doing a better job as far as we can quantify identifying some wetland extents that are just missing from NWI data, regardless of whether the landscape changed or not. I think the best illustration of that is the topmost row, where NWI has a linear stream feature, but you can very clearly see an emergent wetland that the model predictions in purple catch. So big picture, as I said, we are using this model. We've applied it to, I think, 16 counties in the watershed. So producing updated wetland data at a county scale. What that can look like is, this is a zoomed in area in Lancaster County, Pennsylvania. These are the existing NWI data. We take the same area, we run it through a model. And these are the wetlands that we're able to map and identify. So we're very excited about these data. Currently, we are working with land trusts that are wanting to prioritize parcel protection based on where wetlands may or may not exist, as well as some utility companies. Actually, Baltimore Gas and Electric approached us because they think these data may help them be more efficient and effective in implementing their environmental compliance requirements under various state and federal laws. So I wanted to share really quickly that we also have made these wetland data publicly viewable. They're not available for download yet, but I can provide a link to this viewer in the chat, and this will give a better sense of the extent of the different counties that we've produced this high resolution wetland data for, some of which are in Maryland. I think we have Howard County and Frederick County at the moment. So yeah, we're very excited about those wetland data. We've just released them and are fielding a lot of interest, like I said, from different groups and frankly some non-traditional partners. Like I said, utility companies are not a sector that we've worked with in the past, but we saw an opportunity to use those data to improve conservation through a different route, and they saw an opportunity to basically save money, I think, if they can be more targeted and effective in where they're sending out crews on the ground to delineate wetlands ahead of things like right-of-way, transmission line creation, and maintenance. Our wetland data are very closely related to the third data set that I wanted to share. This is one that I think is folks that are in water modeling and hydrography circles get really excited about, and I've noticed that folks that are not in that world are less familiar, but I think it's one of the more powerful data sets that we've developed, and this is what we're calling hyper-resolution hydrography. It came from a collaboration between the Bay program and Matt Baker's lab at UMBC. And in a nutshell, what we were able to do is map more completely and accurately the stream network, including small headwater streams and small channels throughout the Chesapeake Bay watershed, using a really novel, innovative approach. So we took digital elevation data and categorized those DEM pixels into something called geomorphons, which characterizing what type of landform each pixel is. Are you a flat area? Are you a ridge, a valley, a side slope? And then from those geomorphons, from this high resolution digital elevation data, we were able to then create polygons that identify stream channels. So it's a fundamentally different approach to the way that many stream, like linear stream network features are built. And it's been able to map about 2.5 times as many stream miles as the existing NHD data, as well as providing a two-dimensional polygonized representation of stream channels. So there's much more information in these data than might exist in a line feature. And so just an example of what that comparison looked like. This is a snapshot from our viewer that provides access to these data if folks are interested. You're seeing an example of existing NHD, National Hydrography Dataset data in yellow. And these are all the stream channels that the hyper-resolution hydrography data identifies. So I'll do that swipe over once more. And like I said, there's about 2.5 times as many stream miles identified. And these are often in places that have outsized impact in terms of inputs to the stream network. They're the headwater streams that are often intersecting agricultural fields. They're roadside dishes that are collecting runoff, small features of that nature that are often missed, but need to be accounted for if you're doing any type of water quality modeling. So an example, one of the cases that we've been putting these data most to use is in our work in Pennsylvania, trying to encourage best management practices in agricultural settings, specifically for livestock. And so the image you're showing here illustrates, I think, the use case that I was just describing. You can see down in the bottom of the screen, the red line is the existing NHD flow line for what looks like the maybe a secondary stream. The yellow area is that polygonized representation of the stream channel that we were able to extract from the digital elevation data. And then the blue line is our linear characterization of that stream channel. So the important thing I think to notice here is that the NHD line is pretty much limited to that, lower right portion of the map. And you can see in the upper left portion, we've got some sort of, livestock animal feeding operation. And if you were just using the NHD data, you might think that there was much greater separation and buffering between whatever is coming out of that animal feeding operation and the stream network. But our data show that there's actually a stream channel that runs right through much of the either grazing or crop field, and then basically right up next to the animal feeding infrastructure. So this would really drastically change both our understanding of nutrient loading going into the stream, and also identify an additional area for best management practices to try to reduce inputs to the stream network. Here's another very similar example. This time, I don't know that they're necessarily confirmed livestock, excuse me, being kept here. Actually, yes, there is. And again, we're able to account for a much more detailed and comprehensive set of inputs to the stream network. In this case, we've got another stream channel that's basically draining a pasture where you've got livestock into the stream. And so these data are available for the entire Chesapeake Bay watershed, wall to wall. They're available through the viewer. They can also be downloaded, I believe, from that same link. Changing gears as I wrap up and provide our sneak peek into the future, moving out of the sort of water world of wetlands and hydrography. I thought that, this group being focused a lot on climate scenarios and mitigating effects of climate change might be interested in a new capability that we're developing, which is basically to provide improvements to the existing Chesapeake Bay land change model. So for those that are familiar, this is the model that the Bay program uses to forecast different scenarios of commercial and residential development in order to anticipate nutrient loading and guide the placement of best management practices, permitting, things like that in the future. So what we are trying to do is take, a snapshot or a past history of the landscape, like what you're seeing here on the eastern portion of Delaware, where we've got impervious areas, existing impervious areas in gray, agricultural lands in yellow, forested, or otherwise natural land cover in green. And the model is aiming to identify at 10-year time steps, this is 2020, where in 2030 are we going to see new impervious cover, so commercial or residential development, and be able to do that in multiple time steps. So not only 2030, but 2040, 2050, et cetera, to try to forecast where we're going to see that type of build out of human land use. And so the reason that the Bay program approached us to try to upgrade this model is they identified a few challenges that they were seeing. They were seeing over prediction in, quote, rural areas. So there was a lot of development being predicted in places that, they and other experts sort of knew just were unrealistic. The existing model also uses a very coarse rural versus urban distinction and actually fits two predictive models to those categories. And geographers of the Bay program, we folks on this call know that the contexts that drive development are much more of a gradient, a continuous gradient with much more variability than just that sort of coarse binary distinction. So we wanted to see if we could capture that context a little better. And then also we wanted to try to address this path dependence and growth patterns. Basically, whatever your characteristics are at a location in time step 1, 2020 in the example, would determine your growth trajectory. But ideally, the model would incorporate feedbacks that as things change in subsequent time steps, that changes the landscape context, and that should change the likelihood that any given patch gets developed in the future. So the objectives of this pilot project were to basically address and try to improve all three of those limitations. And so we took a deep learning approach to do this, at kind of a creative hybrid modeling approach that consisted of two components. The first one is a self-organizing map, a clustering algorithm that's looking at socioeconomic data to try to describe the different types of places in the watershed. So this is addressing that rural-urban distinction. And so we trained a model that used a time series of socioeconomic data from various sources and basically clustered counties and then census blocks into types without any preconceived notion about what we thought different types were. So this is an organic identification of places that have similar characteristics in these variables through time. This was an interesting analysis in and of itself, but ultimately what we wanted to do was use that characterization as a variable to predict the probability of transition to commercial residential development. And so the outputs from those clustering models were combined with the outputs from a model that takes geospatial data in a time series to create that probability surface. So the bottom section of this diagram is showing the time series model ingesting multiple geospatial variables. I'll describe those on the next slide. Combining those with the outputs from the clustering analysis that's characterizing what type of place any given census block is, and then producing a probability surface in which each pixel is predicting the likelihood that it transitions from some sort of undeveloped to developed land cover. So our clustering algorithm created 66 different types of census blocks. We're still trying to analyze, how we can describe those types of blocks, but we have done a quick post-hoc analysis and seen that there are significant differences in the likelihood of development among those census blocks. So this is encouraging and indicates that we've actually captured some meaningful variation in those places that corresponds to the probability of development. We're combining that, like I said, with these other geospatial variables. So these are describing basically the built infrastructure and physical geography of every pixel. So you've got, proximity to water and sewer, urban centers, as well as travel time, roads, the land cover, all the things that sort of characterize we think capture the likelihood that a given pixel is going to develop. And we conducted this, we gathered these data to create an initial probability surface for Delaware. So what we're doing at each of these points that I've shown here is taking a time series of those predictor variables. So 2 years, 2000 and 2010. We have the values for all those variables. And we paired that with the observed change in impervious cover in 2020. So we're training a model to look at time 0, time 1, and then predict what's going to happen in time 2. And the initial results are pretty encouraging. So what you're seeing here is the existing probability surface that the Bay program uses for Delaware to predict commercial development. And here's a probability surface that this new approach produces. And at this scale, what I think stands out, what I want to notice is that challenge of overprediction in rural areas. We see a lot of yellow places indicating high likelihood of conversion in the existing model. Those get much more narrowed down and refined using the improved AI-based model that we've developed for the Bay program. And if we look in detail, we can see that the predictions in yellow correspond very tightly to places where we saw observed development in red. So we think that this approach is addressing that concern of sort of really restricting where growth is predicted to happen to the places where it is actually most likely to happen. So the model outputs probabilities for commercial as well as residential development. Same illustration here. Here's the existing residential probability surface, relatively diffuse across Delaware in terms of where high probability exists. And if we look at the updated AI-based model, we see, again, much more refined, spatially limited areas where residential development can occur. And our initial post-hoc analysis of these patterns is showing very tight correspondence to where observed residential development actually happened. So we are excited to continue refining this model, and the next step is to scale it up. It has to be implemented across the entire Bay watershed. So we're in the process of curating the data sets from other states in order to train a model that makes predictions not only for Delaware, but for every other state in the watershed. So I'll stop there. Appreciate everybody listening. Hope the data sets that I'm sharing are relevant and spark some ideas, and hopefully we have time for questions or discussion.
Yeah, thank you, Mike. Yeah, I mean, thanks for showing very cool tools. So one question is, how scalable are these two? So you know, can we do this whole state of Maryland? Is this just for the Bay? I mean, what's the feasibility of scaling this up?
Yeah, are you curious about one in particular, or one data set in particular, or sort of all of them?
Yeah, all of them, and yeah, more conceptually now than getting deep into each of one of the tools, but more conceptually.
Yeah, so I think the land cover land use data exists for the whole watershed. So that's not the entirety of states necessarily, but it is for the whole watershed.
Oh, yeah, okay. So
the hydrography data, those stream channels that I mentioned, exist for the whole watershed. So we feel like we've effectively scaled those already, at least in the region that we work. We've developed the pipeline to produce wetland data in a county size area in a matter of, half a day, a couple hours. So that would take some just dedicated computing time and resources if we wanted to, pool together and create those data wall to wall for the watershed. We've got, I think, the infrastructure built to do that, and it would take just a little bit of investment of time in cloud computing. And then, yeah, the real challenge for the land use forecasting model is just curating all those input data sets that I mentioned. So like distance to roads, distance to water. And fortunately, the Bay program has had to do that for their old versions. So they are working on basically running their automated scripts to do that. So I think to answer your question more briefly, 2 data sets are scaled, and we've got the workflow to scale the other 2, I think, in place, provided sort of time and resource investment.
Okay. Are these data sets being used in any sort of modeling at this point? Is anybody like using this yeah?
Yeah, so the land use land cover data are used by the Chesapeake Bay program in, I think, all of their water quality modeling tools. The watershed model, I think as they call it, that's analyzing and predicting in sort of real-time nutrient loading to the bay. I don't know that the hydrography data set are being used in models yet. I think Matt Baker's got some ideas for how that might be used, but that's worth us getting underway. Yeah, it's something that I think is the next step for them, and would be really interested if there's ideas from this group how it can be done. There've been a lot of prioritization, characterizing analyses so far, but I think a lot of the real power of data like this would be in modeling.
Yeah, there's a couple of questions in the chat, so rather than read them, I'll let Rachel first, and then Adele shoot your questions.
Sure.
Sure. Just wanted to clarify real quick about, I think I heard you when you're talking about the wetland data, just confirming this was non-tidal wetlands that you were attempting to better delineate in your mapping product. Is that right?
Correct.
And then can you remind me what year, approximate year you were sort of dating that new map layer to?
So those would be dated to 2020 or 2021, depending on when NAEP was flowing for a given state.
Right. Okay. So, and then is this going to be included within, is it going to be integrated within the updates to the NLCD data, or is it just operating sort of separately because it's the high res data that you, like you mentioned, you provide for the watershed?
Yeah, the wetland data are separate currently. The goal is in the next agreement with the EPA to update the land cover data to ideally burn those wetland data into the land cover data product as well.
Okay. And then do you anticipate doing a change analysis once you get perhaps new updated NAEP data? I mean, they can have that annually depending on the county, but are you intending to do that as part of your work plan?
It's not something that we've explicitly planned for, scoped out. I think it would be really valuable and interesting. But yeah, we're not explicitly planning on doing that just for the wetland data. Change will be something that is characterized and quantified for the land cover, the next vintage of land cover data.
Okay, great. And part of my interest in these questions is because, of course, we use really high resolution data to inform a lot of the forestry and land use part of our greenhouse gas inventory. So in particular, we use NAEP and high resolution LiDAR to focus on tree and forest cover changes, which I know you all worked on using, well, you also worked with University of Vermont, but you used similar machine learning approaches to do that for tree canopy cover some years back. But just always curious to see how when we do have paths forward on high resolution change data, that can always serve as an additional piece of information we use to kind of track what's happening in that sector as well. So appreciate it.
Yeah, no, good to know. I appreciate you flagging that.
Adele?
Yes, thank you, Fernando. Mike, this is great presentation. You know, as a hydrologist, water quality modeler, I like these stuff, so thank you. So I just couple of, clarifying questions. On the wetland part, what kind of attributes, data attributes for each of the mapped wetlands do you all have? In other words, in terms of, size and vegetation, type of vegetation and so forth, because as you know, that would affect in terms of filtration capacity or even green methane emissions and so on.
Yeah. So the data are coarsely classified into 4 different wetland types. We don't do any description of like the vegetation community or water regime. Basically, 4 types are forested, emergent, or farmed, or open water. So that's as fine resolution as we get to it taxonomically in terms of the type of wetland, is those 4 types. And in terms of characteristics like size and shape, the data are natively output as pixels of probability. So we don't out of the box have those attributes because one has to choose a threshold, which we've done in ROC analysis to identify the one that we think is most appropriate for converting rasters to polygons. At which point you could make those attributes, but yeah, the data are natively a raster, so we don't have things like size and shape attached to them out of the box.
Cool. And the other question I had was on the hydrography data that you all have mapped. I'm just curious. In my class, I use lots of StreamStat, USGS StreamStat stuff that the students delineate the streams from those 7-minute quad sheets and so forth. So how do these hydrographies that you all have produced compare with the existing 7-minute quad sheets of StreamStat data that USGS has? Or have you all looked at it?
Yeah, I don't know that we've done a comparison to the StreamStat data. Most of what we've done is looked at the comparison to NHD as I was describing. But that's a good question, and I think one that I can run by our watershed modeler to see if he has done that comparison. I don't know that we have.
Thank you.
Yeah.
Cindy? Did we lose Cindy or? There she is.
We don't hear you, Cindy. No. Do you want to put your question in the chat, perhaps? And we did hear you earlier when you were introducing yourself.
And so you've got the chat box open and waiting with bated breath.
She's typing it in. If we could-
Okay.
I can read it aloud if that's helpful.
Yeah, please do.
Yeah, so Sydney typed along the lines of understanding the objectives, wondering if there are any considerations relating to renewable energy growth and or smart growth approaches. I might need some clarification around what you're asking there. So yeah.
So, well, I guess maybe I'll just help a little bit. You know, Maryland's got a smart growth plan. You know, where every county has to do water and sewer planning associated with their growth plan, amongst other development goals. And you know, I think if I were to be asking this question, would sort of be as you're looking at the development that's currently there, particularly newer development, how would you? Is this a way to kind of scorecard how well those plans are being followed and how well the county's following its objectives? So I changed Cindy's question a bit, so, but I'm just trying to fill in a couple things there.
Yeah. Let's see, she just sent
Yeah. There you go. She was a little bit more on the 8 planning principles, a little bit more detailed on the 8 planning.
Okay, so is that related to what you're just describing, Dave?
Yeah, pretty much. She had more detail in it than I did, but yes.
Yeah. So I certainly think that I'm less familiar with these smart growth goals, so I can basically share my opinion based on what you all just provided. So I do think that, you know, one idea that comes to mind is the land use, land cover data would be an effective way to assess whether those plans were adhered to or goals were adhered to, because we are tracking where there's different forms of new land use about every 3 years. The other thing that comes to mind in terms of how this might intersect is with the land change model, the last data set that I shared. So currently that looks at existing time series of patterns of development along with the socioeconomic characterization of places in a time series to predict future scenarios. But it does not incorporate explicitly any like policy information. There's no zoning that goes in. You know, Maryland has these requirements for smart growth. We would love to build that information into the model as well. And it's kind of a really intriguing but hairy problem to wrestle with, how you would automatically extract sort of like policies that guide land use. We have an idea conceptually how you would do it, how you would put it into practice in terms of aggregating that information from all the disparate municipalities across the watershed is the real bear. But I would love to follow up, I think, on this if anything that I'm saying is hitting at sort of the spirit of this question, because I think, you know, we can, like I said, we can evaluate whether the guidelines have been followed on the back end retrospectively, but we would love to be able to incorporate them proactively to see how they affect trajectories of growth, and as like a scenario planning tool. So that's, yeah, something I think would be worth a follow-up discussion from my perspective. Can you let me know if I totally missed the mark on what you were asking there?
It seems good. She said she'll follow up with you after the meeting. Thanks. I think, Fernando, if there are no other questions on this one, we could probably move on. I think you're more than welcome to stay. These are public meetings, so feel free if you wish. You'll be hearing about some other scenarios related to zero emission planning next.
Yeah, I'll join the listeners.
Yeah.
Sure.
Dave, is that my cue? Do you
That
want
was
to
your
do it?
cue, Mark. Yeah.
Okay. Well, hey, everybody. As I mentioned earlier, Mark Stewart, Climate Change Program Manager at MDE. And I wanted to bring kind of a big policy question to you all, not in the hopes that we will solve it today. That would be wonderful if we did, but more to set the stage for a future conversation and really to gauge your interest as the STWG in providing input on this question that I'll present. So my objective is just to lay out the issue and the question, and then perhaps we can have a quick conversation about your thoughts on how STWG could engage in helping us answer this question. So by way of quick background, and I think that this is not news to any of you, but MDE, we developed the state's GHG inventory, and we developed that in a way that we think aligns with the statutory definitions for statewide greenhouse gas emissions. So Maryland statute says that statewide greenhouse gas emissions are essentially all of the emissions, and I'll add, although this isn't in statute, and emissions sinks that exist within the geographic boundaries of Maryland. So it's in-state emissions and sinks, plus electricity, or plus the emissions associated with the electricity that is consumed in the state but generated outside of the state. So in other words, when you think about our emissions inventory, and this is where it's all heading, our emissions goals, we calculate that based on the emissions that occur in the state as if there was a bubble over the geographic boundaries of the state, and looking at the emissions and the sinks that occur within that bubble, and then adding in the emissions from outside of the state associated with the electricity that is produced and consumed, produced outside the state but consumed inside the state. So those are the basic boundaries that we use. And very importantly, Maryland has a law that says that we need to achieve net zero statewide greenhouse gas emissions by 2045. And the net zero plan is due in 2030. And believe it or not, the construction of that final plan and the pieces that we need to get in place to develop that plan are really, these are things that we need to begin implementing now, just even to set up the analytical framework to develop the final plan. So basically, we imagine that 2029 is going to be a significant modeling year, which just for the fun of it means that 2028 is a fun contracting year for us at least. And 2027 is probably when we need to structure the scope of that contract and the scope of the study to inform the plan. In other words, if there were going to be any revision, any additional thought about what do we mean by net zero emissions in the state, the window to inform that is actually pretty tight. The next couple of years really is our window to think about that before we need to shape up the architecture of the state's net zero plan. And here's the real issue. I'm going to screen share. It's really just one image that we have from our climate plan, but it kind of encapsulates the issue here. Let's see. Is that showing okay on your side? Are you seeing a graph? Okay, great. So what you're seeing is a graph from our climate plan that shows the emissions trajectory under our current policy scenario. And I don't mean to get into the weeds on what are all the federal and state policies that were included in our current policy scenario and how relevant is all of that today. Let's attempt to park that big question for now. But importantly, when we look at our what we call really our plan scenario, the current and planned policies, a few people from the STWG and the mitigation working group have pointed out that under the current plus planned policies scenario, and this is the scenario that would achieve net zero greenhouse gas emissions as currently defined, right? This the objective that the model had in this case, that the University of Maryland Center for Global Sustainability used, was to figure out what is the lowest cost pathway for Maryland to achieve net zero emissions per our definitions of net zero emissions. And one of the implications of this modeling activity, and let me attempt to zoom in, maybe it might help see this a little bit better. And this is the thing that a few people have asked us about and questioned the validity of. At the very bottom of the graph, on sort of the carbon removal side, you see CO2 removal, this red bar of CO2 removal at the bottom. And what is that? That's basically in the modeling environment. The model said that the lowest cost pathway for Maryland to achieve net zero emissions by 2045 is to significantly reduce emissions from across the different sectors of our economy. But at some point, it becomes lower cost to build CO2 removal technology than to squeeze out the last bit of emission sources in the state. CO2 removal technology might be one that you all are familiar with and have discussed it as STWG, but one example of this would be direct air capture technology that exists to pull CO2 out of the atmosphere and sequester it in solid form. Solid or gaseous form, but basically pull it out of the atmosphere, right? That is a technology that is fairly expensive to build and operate, and yet, in terms of thinking about the challenges of achieving net zero emissions, the model anticipates that it would be lower cost to build that technology and deploy it in Maryland than to achieve, the last mile of emissions reductions. Now, of course, there's some improvements that we can make to the model and the assumptions and the cost estimates, but I think that result, that modeling result, has caused some people to question if there were to be an investment in CO2 removal technology, assuming that is part of a net zero emissions solution, would that be best deployed in Maryland? Frankly, it's lower cost to deploy this type of technology in places with very cheap, clean electricity. And hopefully cheap, clean electricity is Maryland's future too. But just in terms of where we're seeing this deployed right now, it's Iceland and other places that have different resources than Maryland has. But even to contemplate in the modeling environment, what would it mean for Maryland to deploy technology beyond the borders of Maryland introduces some new framework that we would need to use to even think about the question that we're trying to answer. What's the most cost-effective way to achieve net zero emissions as a state? So the big policy question that we have for you, in statute, the statute says that as we develop our policies to achieve the state's emissions goals, we can include the consideration of carbon credits so that reductions in one sector could help entities in another sector achieve certain policy goals. But in statute, that's also envisioned to be still within the borders of Maryland, right? All activity occurring in state. So as we think very generically about the objective of reducing CO2 emissions and tackling global climate change, of course, where the emission reductions occur in the world don't much matter. It matters that the emissions are being reduced, that carbon sequestration is enhancing, and that globally we're approaching net zero emissions, right? So from the global climate perspective, it doesn't much matter where it's happening. It does, once you introduce the economic lens, it does matter that that's happening in an economically efficient way. But as we of course dig deeper into the economic lens, we realize, well, deploying these activities, using these measures in Maryland has economic benefits to Maryland, right? As we deploy these things, it creates jobs here. It has other co-pollutant benefits, public health benefits that occur here. So I think it's for good reason that the law that we operate under envisions achieving net zero emissions within the borders of Maryland. And yet, because we've been going through this modeling exercise with our modeling team at the Center for Global Sustainability, and we end up in the modeling environment, at least, with a really significant build out. I mean, we're looking at more than 10 million tons of CO2 removal through CO2 removal technologies by 2045. That is a significant consideration as we think about what do we mean by net zero emissions as a state? What's the framework that we want to use to design our policies to achieve that goal? And I just wanted to bring that question to you because it's a big policy question. It's a policy question that largely would be answered and addressed, we think legislatively, but the Climate Commission is designed to advise the legislature on these big policy issues. And the degree to which the STWG would love to weigh in on this debate that I think is also going to unfold at the mitigation working group this year. That's really where I wanted to get some input to find out, is this a topic that you all would want to engage on? Dr. Bosch?
Thanks, Mark. I'm glad this issue's been raised because when I read the initial framework report and the pathway report and then the plan, it's sort of like you see that little red part at the end. It's like, poof, a miracle happens, that we're going to find these additional sources. So it seems to me it's a complex issue. It involves a number of things in addition to direct carbon capture, from the atmosphere. So, for example, there's a question of whether the more can be wrung out of natural systems storage. That green part can that actually be part of it? Number one. The second part of it deals with carbon capture as a result of emissions processes. The way it's set up, and including the actions of the General Assembly this past session to open the door to more natural gas production of energy, of electricity, and with the proviso that somehow it'll become neutral, in the end. The use of hydrogen, which would probably have to require carbon capture and storage from that system. So there's that part of it, in terms of capturing the carbon at the point of combustion or near the point of combustion and subsurface injection or something or other. And then there are the issues of atmospheric carbon capture, which, as you pointed out, would probably not necessarily be most efficient or done most effectively within the state borders. So they include things like, there's a lot of research on the ocean sequestration of carbon in the ocean. And that's going to have to require some sort of an international framework that's going to involve who pays for that. So I think it leads us to a consideration of yes, it makes sense that some of the carbon removal is done outside of the boundaries, but there has to be some sort of a nexus of connection, cost to payment for the cost or something like that. That's part of it. The other part of it I want to make is that we're not in this issue alone. Everyone's trying to figure this out. So there are a number of reports which maybe we can help you with. The National Academies have been particularly helpful. They've done a series of studies. I've shared earlier ones with you all some years ago about accelerating decarbonization, things of that sort, that we can help you by looking at the global literature and other assessments that have been done to help kind of understand the nature of this challenge.
Great. Thank you. That's really helpful. And just taking some notes here as we go. Sure. I lost track of hands. James, were you next up?
I think so. Yeah, thanks. I wanted to point out that there are not only scientific and technical issues related to carbon removal techniques and the use of offsets, but there are also a lot of other issues such as related to well, environmental side effects, but also social concerns and ethical and governance issues. And so I think it should be. It would be important to try to bring social scientists into this discussion as well regarding how to achieve net zero and whether or not to really use and deploy these large scale carbon dioxide removal techniques.
Yeah, thanks. And of course, I didn't mean to overemphasize the CO2 removal. If the objective were to reduce emissions to net zero within the geographic boundaries of the state, perhaps if the model is correct, perhaps CO2 removal would be part of that solution. If there were, and I think Don pointed out a good point about the nexus. There really needs to be, I think, a very strong nexus. But if there were, linked carbon markets where activities that were occurring, financial activities that were occurring in Maryland, were leading to emission reduction projects in other places in the world, with a very strong nexus where Maryland's investment was, driving down those emissions elsewhere. That transfer could lead to greater social benefits, could result in solutions that look a little bit more like the solutions that we often think about, right? Helping people electrify their homes or whatever it is, that winds up being lower cost than CO2 removal technology and preventing the build out of CO2 removal technology. But we would have to be acknowledging this willingness for Maryland's policies to be somehow transferring Maryland investment to other places in order to achieve the lowest cost emissions reductions for the global good, right? Sorry, hands wise, I think Scott, maybe you were next.
Yeah, maybe I think so. Yeah, Mark, thanks for the great discussion presentation there. So I'm an economist by training. I appreciate the conversation about economic efficiency. When we're dealing with a global environmental challenge, and we're thinking about economic efficiency, it does matter. We want to find, ideally, places where have the lowest cost of achieving the emission reductions and find places that have the lowest cost of doing the carbon removal. But, we've set state goals and have policies that don't really engage with that reality, nor maybe can the policy. It is the state of Maryland, after all. So it's a tricky situation. Regarding another observation here regarding the issue of jobs, and this is when you're talking about economic efficiency, that has a technical meaning for economists, and jobs are an input to a production process. So we all want jobs, right? If it goes without saying, jobs refer, that's economic activity. But in an ideal world, we'd like, if we could solve this problem without creating any new jobs, and then have those jobs do something else that's valuable, that would be the most amazing situation you could imagine, right? So there is economists will note this. There's a concern when you start thinking about, well, how can we create like millions of jobs to do this thing? Well, that's not necessarily it certainly wouldn't be the most efficient use of resources, right? So there is like an inherent tension to like creating lots and lots of jobs to do this. And of course, folks at the state, local levels, national levels, they're interested in their region. They care about whether their constituents have jobs. So that is obviously an issue of concern. I'm not saying it's not. It's just there is an attention because from an economic efficiency perspective, jobs are a cost, not a benefit, right? Just want to make that point. I think it sometimes flies under the radar, but Yeah, so I think to the extent we can find lowest cost ways of reducing emissions and removing carbon by partnerships with other, low cost entities in other states, other countries, that would be fantastic. Let's try to do this at the lowest cost possible. Yeah.
Yep. I'm with you. Bill?
I love this challenge that you're giving us, Mark, to investigate these carbon capture approaches. I think that's something that STWG can really sink their teeth into. There is a currently funded project by a NOAA-funded project that Jeremy Testa and from Chesapeake Biological Lab and Ming Li from Horn Point on quantifying the efficacy of wastewater alkalinity enhancement on marine carbon dioxide removal and acidification mitigation. They're partnering with Hampton Roads and Charles Bott, and they're doing large-scale experiment on the sewage effluent. And basically, I think the way I kind of understand it, I think I'd love to get them in to talk to us. But my superficial understanding is if you release water from sewage that's stained with dissolved organic carbon, it becomes which is very refractory and enters the ocean and pretty much sequestered, that you could really enhance our carbon capture capability. And our sewage engineers in our region are among the world's best at removing nutrients. If we can just turn their attention to removing carbon as well, there's a real chance for progress in Maryland itself.
Bill, that makes me think of a couple things. One is that as we head toward the modeling activity, the development of the net zero plan and the modeling parameters, the more that we know, the more that our modeling team knows about the cost, what we call, of course, in the marginal abatement cost of different solutions to reduce or sequester emissions. Factoring those into the model, if we have local examples, real world examples of the cost of doing X, Y, or Z, I think that we can talk with the modeling team about incorporating those in so that maybe the next run of the model, instead of its solution to deploy CO2 removal technology at an assumed price point, $150 a ton or whatever, if there are other options that the model has to deploy other solutions, I think that would be interesting to see how the model at least anticipates the deployment of those, which, assuming the availability of carbon markets, that is instructive to us to think about where would that money go, who would benefit, what would the projects be that would be deployed in those cases.
I think the finance, the thing about sewage treatment is pretty well calculated. You can get pretty good economic evaluations of that, probably.
Hey, Mark, I just wanted to add real quick and for the group too, that the economists, it's not all we think about as efficiency, despite what some folks might say or might believe. Equity considerations are a very important deal here, like who caused the problems, who's solving the problems. I mean, economists have been thinking about these things for a long, long, long time. The equity versus efficiency trade-off, it matters, it's real, it's important, and we can't lose sight of that. Yep.
Thank you. Suzanne?
Yeah, I just, what Bill's point, I thought connected the dots to Scott's economic, there is policy in place to fund actions at wastewater treatment plants. So that eases the path to success for a strategy like that. So for strategies where you have existing policy and funding frameworks in place, those are going to have a higher likelihood of success than, as you suggested earlier, Mark, starting up some kind of air-based carbon capture, figure out how to, build it, power it, and impact it. So that's just something to consider as you contemplate this big picture here.
Thank you. Don?
Yeah, just following this discussion about sewage, this should be pursued and should be looked at, but and indeed we need a whole bunch of options. But I mean, if you first order calculations, this is a small contributor to the reductions that we need to achieve. That red part of that under the curve that we need to achieve is just a sliver. So don't count on it, but think it as one of the options, one of the things we have in the portfolio. But it's not itself sufficient to deal with the scale of this need.
The scale is significant, and we're happy to come back and give you some of our updated. We just shared. Actually, let me share this with you all too, just in the chat. The mitigation working group recently got an update on our preliminary 2023 greenhouse gas emissions inventory, and I'll drop those slides in the chat for you to be able to look at your convenience. But it does help articulate and visualize the scale and sources of the emissions that we have, and by reporting on some of our key progress indicators gives you an indication of kind of where things are, how we're tracking in terms of the change that's needed to achieve our 2031 and 2045 goals. So I'm certainly hearing that there's some interest among STWG members in engaging on this topic of the net zero framework for the state, and seeing that there's interest. I think I've probably heard enough to know that we should figure out how to organize this discussion a little bit better between probably the mitigation working group and the scientific and technical working group, so that those members can really think about, are there recommendations, be it this year or next year. Fortunately, we have a little bit. I'm bringing this topic to you early because I think that we have kind of a 2-year window to think about changes, but especially if the Climate Commission were to make any recommendations on the net zero framework that would require legislative changes, then I think we can all acknowledge that can take a while. So I see more hands up. Adele?
So I think Don sort of in the chat mentioned something about in response to my note about ExxonMobil, but I am hearing, the reason I am putting that is that in any technology that we talk, I think that there has to be a really good overview for the group before we jump into any sort of recommendations and so on, if we are going to tackle this in the future. I personally like to know, I am for finding an optimum methodology, if that's going to be one pathway to go with, whether that's the sequestration on international level, as Don mentioned, in ocean waters or whatever. But what are the other holistic approaches actually that to do carbon capturing and storage? So besides what Exxon, I understand, Don. I mean, Exxon does that to justify their oil drilling, as our current administration says, drill baby drill, which is contrary to what we are talking here. But either way, so my point is, I like really for us to, not all of us are experts in all the areas. So if we need to tackle this, we need to know what the state of technology is, both holistic and yuck technologies and so forth. And then we see, which ones actually can be optimized and used for state. And as a science and tech committee, we need to do that, I think. But thank you.
And we'd welcome input on that. We do fortunately have consultants available to us as we look at the range of technologies and the solutions to feed into the economy-wide plan. So I'd say don't put it on your backs alone to help us understand the range of technologies and their technology readiness. We do have some background on that, but I think the big policy question on whether or not to address this challenge, we should continue to examine a net zero emissions pathway within the geographic boundaries of the state, or more expansive framework with a lot of considerations around what that would look like and the guardrails and safeguards that would be needed as other states in carbon markets, linked carbon markets have mapped out. Is that an approach that you recommend as we evaluate the net zero emissions framework? Rachel?
Yeah, I was just going to flag, I mean, as you all may know, we're a member of the U.S. Climate Alliance, and the Climate Alliance is very soon going to publish a net zero target setting and accounting guide for states based on a lot of work that they've done, collecting sort of examples across the membership, as well as some of the work that their consultants did to help establish that. So certainly that will be a helpful resource for this discussion. We will distribute that, and if there are follow-up questions, about that model, I think they intend to do some separate webinars inviting folks to come learn more about the guide and its framework, but I'm sure they would also be happy to come talk more to this group about that, and that just may be useful for seeing how different states are thinking about that scope.
Great, thanks.
Cindy's got her hand. Okay, or maybe she dropped a comment on the chat too. So
Can you hear me now?
yes,
I don't know what's happening with my sound. Apologies for that. Mark, I'm wondering if you can please speak to the aspect of the law that says that GHG planning efforts in Maryland need to consider economic benefits to the state, and how that could be integrated as we move forward in net zero efforts.
Yeah, I don't think anything that we're talking about is inconsistent with that part of the law. For everyone's awareness, when we develop a plan, we have to do certain economic modeling that shows that it's creating net economic benefits and job growth in the state. So sorry, Scott, to your point, job growth isn't always a positive thing, but per our economic study requirements, we do look for net economic benefits and job growth, net job growth as a result of our planned policies. In many ways, I think that this conversation about the net zero framework would lead to higher net economic benefits in the state, because if we're faced with the alternative of deploying something like a fairly expensive, fairly limited co-benefits technology like
Mark, you froze.
Did we lose Mark? Yeah.
Mark needs to warm up.
Yep. Well, Cindy's working now, but not Mark. So
he was just about to
only one MDE at a time.
Mark, you froze.
Yeah, Mark, I don't know if you want to exit and sign in again, if you can hear us. Oh, no.
Hey, yeah. Sorry, I lost my internet connection at home.
Yeah.
I think that what I was saying, and I'll bring it to a quick conclusion, was just that the changes that I think that we're talking about here would actually enhance the net economic benefits of the state, because it would likely lead to lower cost solutions to reduce global emissions. But there's a lot of consideration layered into that about the co-benefits of these investments and them happening in the state, so that it also challenges us to be more sophisticated as we think about the net economic benefits and how we calculate that. Well, thank you all for your input. I apologize that I had a Wi-Fi wipeout there for a second. But I'll be happy to coordinate with the STWG steering committee as we think about how to further engage and develop this topic.
And Mark, you'll be putting together kind of a group of some experts from the different work groups that are going to kind of help guide some of this modeling moving forward. And we already kind of called for a few volunteers for that, and we could always follow up with you. And then if others want to join in, or if those volunteers are unavailable, I'm sure we could find other interested members. So we could just stay in touch on that moving forward.
Sounds great. Thank you.
All right. Well, we're right on time, so miraculously with these two big topics. So thanks very much, everyone, for participating today. Great discussion. The only comment
We need to have public comment.
Yeah, we have to allow public comment. Yeah.
Let's allow public comment.
Yeah, I don't see any.
All right.
Fernando.
All right. Just on this topic of the net zero analysis, I think the coordination piece is going to be really, really important. So let's not neglect that component, although I'm pretty sure that this is in everyone's minds, but I just wanted to say it out loud. All right, folks. Well, again, thanks for joining. Have a fantastic rest of the day and fantastic weekend, and so we'll see you next time.
Thank you.
Thank you.
Thank you.
Bye.
Thank you all.